For this tutorial, I wanted to look at the problem where we are given a graph and the parent function, and we're asked to find the equation of the graphed function. So in this case, my parent function is the dotted line, and that is the graph of cosine. So I know that I have my parent function, and that is simply y is equal to the cosine of x. You can see that my scale here is in degrees, so the period of cosine, if we trace it out, goes from 0 to 360 degrees, and it has a maximum value of 1, and it has a minimum value of -1. So that's standard parent function for cosine. So now I want to take a look at this other function, the solid line, and I want to think about this other function in terms of, so that's the one I'm tracing out there, we're thinking about that other function in terms of cosine. So there are some easier and more difficult things to look at with regards to this. What I think I'm going to start with is I'm going to outline some important lines in our function. And the first one, let's look at the maximum, which is that line, and the minimum, which is here. So you can see I've got my maximum occurs at 4. So this is the line y equals 4. And my minimum occurs here. This is the line y equals -2. And you could probably tell from this visually, just looking at it, but knowing 4 and knowing -2, we can figure out the point that is halfway between those, and that's known as the axis of the curve. And so that's the first thing that I'm going to figure out in this case. So excuse me. So the axis of the curve is going to be the line y equals, and the way I do that is I simply take the maximum and I add the minimum, and then I divide that by 2. So in this case, the maximum is equal to 4 plus the minimum, which is -2, divided by 2, and that is equal to 4 plus -2 is simply 2. 2 divided by 2 is 1. So the axis of the curve is the line y equals 1. And you could probably see that from the actual drawing. This one's pretty nicely scaled, so that shows up pretty well. So there we go, the axis of the curve, right along the middle there, that is the line y is equal to 1, and that's the axis of the curve. Now from there, we get a couple of pieces of information from that. The fact that the axis of the curve is y equals 1, that tells us a piece of information about our actual equation, and that is that if the axis of the curve is equal to 1, that actually tells us the q value is equal to 1. Now, if I'm referring to q, just in case maybe we need a bit of a refresher, what is the target equation that we're looking for? So our transformed equation is going to take the parent function y equals cosine of x, and that's going to get transformed into y equals, and it's going to be, in general, a cosine k times x minus p plus q. So that's what we're working with here. So the q I'm referring to is obviously the q on the end. Okay, so that comes from the axis of the curve. What other properties can we obtain quite readily from the diagram we have here? Well, if we take a look at the distance from the axis of the curve to the maximum, that distance is 3 units. Or we could look at the distance from the axis of the curve to the minimum, and that is also 3 units. Because I'm just looking at distances, I'm not troubling myself with positive or negative. It's just the idea of an amplitude here. Now, whenever we talk about an amplitude, that means we're talking essentially about the absolute value. So that's how I'm going to record that in this case, which is I'm going to say that the amplitude is equal to, in this case, 3. And what does that actually tell us? How does that convert to a value, well, that tells us that, and I'm going to follow this all the way over, that tells us that the absolute value of the parameter a is equal to 3. So we know the sign of that value, but we don't we know the size of that value, but we don't know the sign of it yet. So those are pretty easy to pull off of here. What else can we get from this? Well, the next thing we're going to look at is going to be the period. So looking at the period, let's refresh our memories once again. The value for, here's the cosine curve, if I just trace that out with the highlighter, and it has a period of 180 degrees. So let's see if we can't find something similar, or sorry, I said 180. This has a period of 360 degrees. So let's see if we can't find something for our solid line, for our new transformed curve. In order to do that, there's a lot of places that we could measure from. One way you can do this is between middle points, but it's actually easier if they're visible on your graph. It's actually easier to get your period by looking at either the distance between the maximums. So for example, there are two maximum points. Those are two adjacent maximum points. So I could take that distance, or I could take the distance between two adjacent minimum points, which is the distance between there to there. And both of those distances are going to be the same. And since my picture is a little bit cluttered on the bottom side, I'm actually going to use the one that I first put in, which is on the top. And so if I measure the distance between these two, and it's arbitrary, they happen to be handy. And if I take a look from here, and if I go down to the x-axis, there's 120 and there's 150, and so that means that the number in between those is 135. And so that means that this is 135. And then I do the same thing down here, and then I'm between 300 and 330, and that number is 315. And so that means this one is 315. So the distance between these is going to be 315 minus 135, and that is equal to 180. And I guess I should be careful. These should all be measured in degrees. Unfortunately, my scale along the bottom from GeoGebra doesn't show up in degrees, but really all of these measurements are in degrees. So I have a period of 180 degrees for my transformed function. So let's go ahead and refer to that. So I'm going to say the period is equal to 180 degrees. Now, how am I going to relate that to these parameters a, k, p, and q? Probably didn't give myself enough room there. So how does that relate? The relationship there is that the period is given by the equation 360 degrees divided by k. And this 360 degrees is the period of the parent function. Maybe I'll just put a little note in there to that effect. So that is the period of the parent function. So that's where that 360 degrees comes from. So we actually, in our equation, we know that the period is 180. So I'm actually going to write this now just as a regular old equation. 180 degrees is equal to 360 degrees divided by k. I get 180 degrees times k is equal to 360 degrees. And so from there I get k is equal to 360 divided by 180. K is equal to 2. So now I've got 3 of my parameters, or maybe you can think of this as 2.5 of my parameters. I have my q value, that one is done. I have my k value, that one is done. My a value, I have the magnitude of the a value, I have the absolute value, but I don't actually know the sign of the a value. And the reason for that is the sign of the a value actually could take on a couple of values here. And while I'm speaking of signs of values, I think I should also point out my k value could have been positive or negative here as well, but for the sake of simplicity, I'm basically going to always, whenever I'm coming up with values for the k value, I'm going to always set my k value to be positive. Because these periodic functions repeat themselves, the choice of a and k being positive is really just a choice of where do I or how do I look at my graph of my function. And so let's take one last look at that graph. And now the thing we have to look at is where does cosine start, or how does cosine start, and how does that compare to our graph? So I'm going to actually lay out for you two scenarios here. In the first scenario, I'm going to choose my starting point. Let's see, I'll choose a different color here. Cosine normally starts here. It normally starts at a maximum, and it starts along the y-axis. So basically it starts along the line x equals 0. So if cosine starts at a maximum and it starts at x equals 0, we can find for our transform function where is it starting at a maximum. And in that case, I could say, oh, there's my starting point right there. And what is the x value at that starting point? That's actually x equals 135 degrees. So I could use that as my starting point, and that's where we get the phase shift. The phase shift is the difference between the starting point of the parent function to the starting point of our transformed function. So I could choose that as my phase shift, which is a phase shift to the right of 135 degrees. So if I go down and I put that in, and I'll use the same color in this case. So here, if I use that light blue, that gives me a phase shift of 135 degrees, or we'll even be saying that's positive 135 degrees. And so how does that particular phase shift translate into a parameter? That's our p value. That's why it has the letter p, and that's going to give us a value p is equal to 135 degrees. So now I actually have, oh, sorry, there's one more thing that I can say now about this, which is, if I go back and look at that, if I take a look at my starting point here, cosine was at a maximum. At my new starting point, cosine is at a maximum. And so for both of those, cosine's at a maximum. That means there is no vertical reflection. And so for that reason, because there's no vertical reflection, so I'm going to add that here, no vertical reflect. And because there's no vertical reflection, what impact does that one have? That actually lets us finalize our value for a, which means that a is actually equal to positive 3. So we were unsure previously about what the sine of a was. Now we know. And so I should be able to, at this point, I should be able to just go ahead and write my equation. My final equation is y is equal to, a is equal to 3. The parent function is cosine. The k value is equal to 2. X, now it's x minus p. So it's x minus positive 135, which is just the same as x minus 135 degrees. And what about our axis of the curve? It's at plus 1, so the q value is 1. So that is my final equation for the graph as shown. Now there's another way I could have looked at this graph, so I want to show that to you as well. So take a look at that equation, make sure that that makes sense to you. But just in case you may look at this situation another way, let me show you another option, which is, I'll choose a different color here. I'm sorry, things are getting pretty messy on here. So once again, here's my starting point at x equals 0. But let's say I know that cosine is at the extrema, which means either at a maximum value or a minimum value. And I might look at my graph and I might say, hold on, there's a minimum value right there. I could start here. So what is that minimum value? That value lines up with 45 degrees. And I could say, oh, okay, well, I'm going to use that as my starting point, which means my phase shift is actually going to be there. And so what result is that going to give me? So I'm just going to switch to another page. And so in the case of this purple one, I have a phase shift, and my phase shift in that case is actually equal to the right by 45 degrees. So that's interesting. Phase shift is to the right by 45 degrees, but here I have a vertical reflection. So think about what that might mean when we express that in terms of our parameters. Well, phase shift to the right by 45 degrees simply means that P is equal to 45 degrees. So the number has changed. A vertical reflection means that the A value is now negative, because instead of it being at the maximum, instead of cosine starting at a maximum, which is normal, it's actually starting at a minimum. And so that's why we now have our A value is negative, and so we end up with a different equation. Y is equal to negative 3 cosine of 2 bracket x minus, now notice there are two changes here. We have the negative 3 has changed and the 45 has changed. The Q value and the K value are the exact same as they were before. Those have not changed. So by making that shift, we end up with a different equation. But this equation is also correct. It also describes that graph. And just to take it one step further, I know it's getting a little messy, but you can stop this, obviously, this tutorial at any time. I'll pick a new color. What if I decided I wanted this to be my starting point? Well, what phase shift is that? If I look down to here, that angle is negative 45 degrees, which means this is my phase shift. It's actually in the negative direction. So what are the implications of that? So again, keeping that color, I have a phase shift equal to, in this case, negative 45 degrees. And do I have a reflection there? No. That means my cosine is starting at the top. Cosine is normally starting at the top. This one's starting at the top. That's no vertical reflection. And so there's no vertical reflection. And so what are the implications of those two statements? The first one, fairly simple, a p-value of negative 45 degrees. And the second one, the implication of that is that my A value, with no reflection, the A value is going to be positive, which means we're back to an A value of positive 3. We write out our equation. This is the last one, I promise. So we end up with 3 times the cosine of 2. Now, it would be x minus p. I'm just going to write this over to the side here. Remember that it's x minus p, which is x minus negative 45 degrees, which is the same as x plus 45 degrees. So understand that that's where that's coming from. And so that is what goes right here, x plus 45 degrees. So a negative value for p results in a positive value here, plus 1. So in this case, the 3 value has changed again. Now we're back to a positive. And now we've got the sign change there. The 2 and the 1 also haven't changed. And once again, this is overall. So all 3 of these equations are equivalent. And that's definitely something we want to So all 3 equations are valid. So that's an interesting result, which is we can get multiple equations, and all we have to do to get those multiple equations is we change our starting point. Hasn't changed the amplitude, changed the sign of the amplitude in one case, but all we've done is by changing the starting point between this blue starting point and this purple starting point and this orange starting point, we've generated 3 different equations just by changing around those starting points. So if you're asked to provide multiple equations, you can always vary the equations because this is a periodic function. You've got many, many starting points here. Last note here is that generally you want to choose your starting point to be as close to the original starting point as possible. So to be honest with you, even though this x equals, or this phase shift of 135 may have been the most obvious choice, my preference for starting points here, if I were to order them, what would be my choice if I was doing this myself? I would probably choose this one first because it's no reflection and it's close to the y-axis. And then I would choose this one because it's there's a reflection here, but it's actually, the distance is quite short. Both of these are only 45 degrees away from the y-axis. This one would be my third choice, and I would not choose this one or this one. And the reason I wouldn't choose either of those two endpoints is that both are more than one period away from the x-axis. So greater than one period from the y-axis. And if it's more than one period from the y-axis, then there must be another point that's closer and better. So I wouldn't use those at all. So I've managed to make a real mess of this diagram, but that's the beauty. You can always rewind, go back and take a look at things, and hopefully that makes some sense to you.